Hi, good evening all. Welcome to live session number 6 for Computational Fluid Dynamics of Incompressible Flows. Myself Durga Prasad, and just a brief recap. So we started out with applications of computational fluid dynamics and governing equations. We classified different kinds of PDEs, elliptic, parabolic, hyperbolic, and then we introduced how to solve them using the finite difference technique. Within that, we covered elliptic, parabolic, and elliptic parabolic equations, and this week we will be discussing about hyperbolic equations. So within hyperbolic equations, we'll start with some examples. How do you classify PDE to be as a hyperbolic PDE? And then again, two classes of methods similar to parabolic equations. In hyperbolic equations, we have time, in addition to space, we have time coordinate. So then we have two different classes of methods, explicit versus implicit methods, depending on how many unknowns we have. Within explicit, so all these terms you will be familiar with to you when we solve the parabolic equations. So for time, you have a forward, and space we have forward, or space you can use central, this is forward, or you can also have time to be central, like we just to split it. We have like either forward, backward, with just within the finite difference formulation, we have different ways of writing, discretizing the domain. So we have forward, backward, and central, like up to second order. So this is first order, and this is second order. So you can choose different combinations: forward time, forward space, forward time, central space, like all the combinations that you can try out with this. We have different ways. But then, as we discussed in parabolic equations, so we also need to consider about the consistency and basically stability of this particular scheme that you have chosen. For hyperbolic equations, certain schemes are not stable. How to do stability analysis is something that we'll discuss next week after the one-human stability analysis is there. But the idea goes like this. So you have a solution, the finite difference solution, and then you have the exact solution. The difference between these two is you will call it as an error term, and you will monitor how the error grows as a function of your iterations or as a function of time. If it keeps increasing, then you would call it as an unstable one. We will restrict we only need methods which are stable, so that error either becomes constant or keeps on reducing. So there are different methods. We will go through one by one within explicit, and then there are a set of implicit methods for which we do not have the stability issues, but we need to just make sure that the delta t is chosen sufficiently small so that the accuracy is maintained. No, this would actually be an explicit method. First, the examples we have the wave equation. So the way to classify hyperbolic, like given a second order PDE as hyperbolic, is you calculate the discriminant b square minus 4ac, and if that is greater than 0, then we'll be having two different characteristic lines, y equals to some c times x and y equals to minus, we'll use a different notation, some beta x and minus beta y, minus beta x, or beta 1, beta 2, whatever it is, depending on the type of equation you have. So where beta 1 or beta in general is beta 1 is plus or beta 2 is minus or whatever, accordingly you can take these values. Then I can just call this beta 2. So for a given second order PD, if we have two different characteristic lines, then we would call that as hyperbolic. In hyperbolic equations, we will have like these characteristic lines are the lines along which information propagates. So unlike parabolic or elliptic equations, information is kind of restricted to a certain domain. So the influence is restricted. While parabolic, it is like the infinite domain. The entire space is influenced simultaneously. Here we'll have a specific region excited for a specific, like the specific domain of influence is present. So examples are like a wave equation. So if you happen to see, let's say have a pond or something, and some drop impinges on the top, you can see some waves. Only within, there will be some slight region. You'll have a peak at the center, and then it gradually diminishes. So this region in between is what I'm calling the region of influence. So this would be the characteristic line. Like if it were a 1D problem, then we would have lines. Accordingly, this changes. Here we would have a surface. The other equation is the advection equation, which is a term that comes in our Navier-Stokes. We'll have u, but let's say if it is constant. Let's say we have a flow where the velocity is maintained constant, and let's consider a scenario like this. So this is some tube or something, and we have some, like we are maintaining constant flow throughout it, and then there is some species that is coming in from the left. So how this species is getting transported within this, the governing equation will be del phi del t plus whatever is the velocity of the constant velocity that we are maintaining here times del phi del x. This would be the equation where diffusion is kind of less dominant if velocity is sufficiently high. So this is an advection equation. Here also we have a certain domain where this is getting influenced, or there is this particular direction in which the information flows. So this is also a kind of a hyperbolic PDE. So all these kinds of PDEs has a certain direction in terms of space and time as well. So when we are, if we were to use say Gauss-Seidel or something, as we discussed before, in Gauss-Seidel iterations, what we were doing is we take information in one point and then we spread it across all. So it's a steady state heat conduction equation. We were doing some update like this. Say for a 2D problem, we have east-west, north and south. So at any given coordinate, we'll start from initial guess, and then we'll keep updating this one. So as this gets updated, the values of any disturbances or any deviations in from the boundary condition, let's say the information at boundary condition, if we have a boundary conditions where we have different temperatures, initially if we initialize everything to be 300, this information from 500 will gradually propagate throughout. But that kind of schemes are not applicable here. So here instead what we will do is the marching, like what we did in parabolic equations, where the domain of influence is also kind of restricted. So if it were a parabolic equation, we will see in the explicit form. Let's say if this is our governing equation, del phi del t is minus c del phi del x. So we define something called lambda, which is a stability criteria, as c times delta t by delta x. You also call this the Courant number. So here how we are doing, the way we update is very similar to the parabolic equation, where phi I n plus 1 is I is the spatial. So I have a grid in the space. So this is my I direction, and let's say this is my time direction. So this is my n plus 1 and n. So del phi del t, you discretize with the first order phi I n plus 1 minus phi I n by delta t equals minus c times. You discretize this again with this is a forward thing. In a forward space, you I plus 1, use the I plus 1 minus I by delta x. This is again first order. So initial, you'll have the initial x comma 0. The values of phi at t equal to 0 will be provided to us. So all we are doing is taking all those values and updating the value of phi at n plus 1. And then we keep marching this in forward. So if you were to rewrite this equation in terms of lambda, just take it on the other side. So it will be something like phi n plus 1 is phi n times 1 minus lambda plus phi plus 1 n times lambda. So the main problem here is we are in order to update the value of phi at the say if you want to update this value at n plus 1, we are actually using the value at I plus 1 and I at the previous time step. But as I said, information only propagates in one direction in hyperbolic equations. So in this particular case, if we assume c to be greater than 0, which means information flows in this direction, in positive x direction and positive time direction. So in order to get the new update for phi, we are actually using information from a coordinate here, which might or might not have the real update available at. So the disturbance might not have propagated until the I plus 1 coordinate the previous time step also. So this we will do a formal analysis also how to calculate stability for this kind of problems. Just to give you an idea of how to do that, let's take the same form. So we have phi n plus 1. So as I said, what we will do is we will assume that let's say the error term will be the exact solution is TE, or there is another alternate way. So we will assume that the harmonic solution exists for this particular problem. So some solution of the form e power a times t something of this form. I'll just write it as phi of x comma t. So what we are trying to understand now is if a solution like this exists and if the value of a is positive, then this keeps increasing as a function of time and this will be an unstable. If a turns out to be negative or equal to 0, then we can call it a stable. So all we have to do now is substitute this back into my grid in like discretized grid. So phi I n plus 1 will be e power at times x plus delta x. Similarly, we have, n plus 1. So I have to write e power a t plus delta t times e power I k x. Phi n will be similarly for phi I plus 1, x will be x plus delta x. Time will be the same because it is phi n. So then we can write this as, let's say I'll call e power a times delta t as, this is basically the rate at which the value is increasing from t to t plus delta t. So if I were to take phi of x comma t plus delta t divided by phi of x comma t, so this is basically e power a times delta t. So I'll call this the growth factor g, or any other name that you can keep. So this will be g. So e power at will get like e power at and e power ikx can be cancelled. So they are basically non-zero values. And then we have e power ik delta x. So now what we try to understand now is whether this quantity z, the magnitude of this quantity, is greater than 1 or less than 1. So e power ik delta x is like, so this is basically something like cos k delta x plus sin k delta I sin k delta x. The modulus of this will always be close to 1, like less than or equal to 1. So the magnitude of this is always less than or equal to 1. And then we have a 1 minus lambda times plus lambda times something that is less than or equal to 1. So what will this quantity be and how to evaluate that is we can do the math rigorously, or just to put it simply, we'll have plus I sin k delta x. And then if you were to calculate mod g, and what we try to do is we'll make this less than or equal to 1 and then find the value of lambda for that. So this is how we do the stability analysis. We will do this, we will find the values of lambda for each of these next week. But I hope the idea is clear. So the idea is basically you assume a certain form of the solution and then see whether the amplitude is actually increasing or decreasing as a function of time. If it keeps increasing, then we call that unstable. So with that idea, if we were to approach for different problems, we have a certain stability criteria for each one of this. So for now, we'll take the values as is and we'll actually solve for them in next week. So for forward time, forward space, it's actually unstable. So physically, the idea is you're trying to access information that is not may or may not be available in at that particular point of time. So this is usually unstable. And then comes instead of forward space, we can take central space also, which will again use information from the next coordinate, like the next grid point. So this is also unstable in nature. The only like instead of a forward one, you can use a central second order accurate scheme. And then the third one is called upwinding. The idea here is we know as I said now, information we always need to take information from where it is available. So for example, if the flow direction is along positive x, so I need to be only using the values of grids behind this one, which are already available. So the information is propagating only in this direction, so I need to use grid points in this direction. Similarly, if the flow is happening in reverse direction, in the negative x direction, I need to use information from the other direction. So depending on that, this switching will automatically happen. So when you have C as positive, then this quantity will just go to 0. So it will not take a phi plus 1, it will only take phi and phi minus 1. So this one will switch to a backward space. And if C is negative, then this quantity will go to 0 and this one will get turned on. So this is basically like TF, the forward space scheme. Again for this, so this is actually a stable scheme, but it is first order in time and space. And there are other problems with this particular scheme. The upwinding scheme is what we call a diffusion error. So if we were to take this, so what is diffusion error? Is let's say we have this equation, and we are talking in terms of t. So let's say Pt minus c times Vx equals to 0, and we are using some upwinding scheme, assuming c is positive. Assume c is positive, then we have Cin plus 1. So for upwinding, c is positive, which means I have to use the information from the previous cell, like information is propagating in this direction. So I should not use this cell. I should be using the one behind it. So my scheme will be phi n minus phi minus 1 n by delta x. So what we do now is we try to understand the error for this. So we do a Taylor series expansion. So phi n plus 1 is phi n plus pt times delta t plus some other higher order terms. And similarly, we have phi minus 1 n plus some higher order terms. We substitute them back. So this will be pt, like dividing by delta t. So this will be order of delta t. And we have phi n minus phi n minus 1. This will give me a phi x delta x. Yes. So if I were to collect the terms together, so I have a phi t minus c times phi x. I can actually convert it into a little slightly different way. Okay, there is a pi delta x term here. So we have phi t minus c times phi x. This is my original equation, but in addition to that, I am having an additional equation which is c times delta x square by 2 phi xx plus my higher order terms. What this additional term is, if you were to look this equation very similar to, let's say, our Navier-Stokes equation, instead of p we'll be having del u del t minus, instead of c we'll be having u del x, plus this term you can consider this as nu times del square u del x square. Did I missing sign somewhere? phi I minus phi n minus 1 is px times delta x minus px. Yeah, something of this sort. I think I missed some sign somewhere. If you can find me, let me know. This has to be plus, I think. Yeah, but the idea is similar to this one. So this equation you can compare with the Navier-Stokes equation, and you can see that there is a term that is appearing here, which is very similar to the viscosity term in our Navier-Stokes equation. So this is what we are calling the dissipation error. And this dissipation error is a function of the C and delta x square. So depending on your spatial grid discretization, your dissipation error will actually be a function of it. So if your spatial grid is not accurate enough, then you will see the dissipation. So what does dissipation mean here is just like in real fluids, if you increase the value of mu, what happens is it will mix up the things. So more mixing will happen. So instead of having some sharp, like say you have say this is what you are expecting something to be, really will not have a, like we'll have some continuous function, will not have a sudden step change anywhere. But when we use a discretization like this, then it will cause some dissipation, so it will cause some mixing here and here, so it will kind of smoothen out. So this is called the dissipation error. Now and that is happening because we are using because we are having this pxx term here. So then comes the next method called the lax method. So here, instead of using first order in space, we are using again a second order in space. And then we are doing one more trick here to eliminate the, so if you compare this one and this one, the only difference you see here for phi n, we are actually now using an average value of phi plus 1 and I minus 1. So what this does is, if you do the Taylor series expansion, you'll understand that this is actually stable with lambda less than or equal to 1. Again, we will do that next week in the von Neumann analysis. The approach is very similar to this. So you assume a particular form and then substitute it into our finite difference form, and then try to evaluate the magnitude of mod g and see whether it is less than or equal to 1 or not. If it is less than or equal to 1, then we would call it as a stable method. And for this particular method, it turns out to be less than or equal to 1. But you can see the similarity between forward time and central space. So intuitively, how to understand that is, if you are using only the information from the future values, then it becomes unstable because this value might not exist at that particular point of time. So we are using an average of these values. So we are basically giving some weightage to future and more weightage to the past or something of that sort, which will kind of give us a more stable solution. But all of these are explicit, so they have certain criteria on the values of lambda, and this lambda is delta t by delta x. So let's say if you have chosen this particular method, then what happens is, in order to reduce your dissipation error, you have to reduce your delta x. So if delta x is reduced, then delta t also has to be sufficiently reduced. Otherwise, lambda will become greater than 1, and then the method becomes unstable. So the dependence between delta x and delta t is not always physical, but more from a numerical point of view this is coming. So we usually use the implicit methods where we do not have such limitations. So in implicit method, let's say okay, we still have second order methods. Let's go to implicit first. So in implicit methods, this is very similar to what we did for parabolic equations. We use a backward time and central space. So the only difference is for the diffusion, for the advection term, we will use the coordinates at n plus 1 time. So now what will happen is, if I were to write this, so we have phi n plus 1 minus phi n is minus lambda times phi plus 1 n plus 1 minus phi minus 1 n plus 1. So this is central space. So all these n plus 1 values are unknowns to us. So we'll have multiple unknowns in any given coordinate. So we'll write this for all the grid points, and then we will solve them simultaneously. So if I were to write this in a matrix form, so this will become minus lambda times phi minus 1 n plus 1 plus phi n plus 1 plus lambda times phi plus 1 n plus 1 is phi n. So this is basically the tridiagonal form that we discussed last week. So all the diagonal elements will be 1, and then the off diagonal. So if you were to write this, so all the diagonal elements pi's will be 1, and then the other diagonals I plus 1 diagonals will be lambdas, I minus 1 diagonals will be minus lambdas. So this is some tridiagonal form. So you can use Thomas algorithm, and then you can solve this set of equations. Then that will give us the values of Pi at n plus 1. So this will basically be matrix A, which is a tridiagonal matrix, times matrix P, which is the matrix P, where B is the values from the previous iteration. And we keep updating, like you can solve this using direct or any other methods that we discussed previously. In order to get second order accuracy, we can use a Crank-Nicolson scheme. This also we discussed in the parabolic equations. This is very similar to the one that we are in parabolic equations. You can also give weightages for both. So you have use a weighted average values of the backward time and forward time speeds. Sorry, backward space and backward and forward time. So this will be n plus 1, which is it will become a truly backward time one, or this is what we were using in case of a forward time method. So you use a weighted average of this quantity. If the weightage is same half for both, then it is the Crank-Nicolson. You can change the weightages. Say you can give higher weightage to this one, say 0.9, and let's say 0.1 for this, and accordingly adjust this value. So instead of c by 2, you put c times 0.9 times this plus 0.1 times this, or any other weightage that you can try, depending on. So the weightage will decide the value of lambda for this. So if you use a very high value for the implicit method, or even up to 0.5, this becomes a stable method. But if you use a lower values for this and higher values for this, then it becomes conditionally stable. And what is the value of lambda for that? Like once the techniques become clear, you can use that. But as it's, we will see some limitations of the stability methods also, how to analyze the stability. But the idea is the same. So this is a second order time in second order in space. This is the one that we usually use for all the solvers mostly. So similarly, for explicit, we also have second order methods. The first one is the midpoint leapfrog method. So what the idea is, just like in forward space or central space, we are using I plus 1, I minus 1 by 2 delta x. We do the similar thing in time. So phi n plus 1 minus n minus 1 by 2 delta t. Then it becomes a second order in time. The only problem with this approach is in order to update n plus 1, we are requiring n minus 1. So which means at initial value, if I were given phi at 0, it just that would just not be sufficient to calculate phi 1. I would need at least phi 0 and phi 1. Then I can proceed to phi 2 and so on. So what we usually do is you from phi 0 to phi 1, we'll use a first order method, and then use phi 0, phi 1, then use this method to next step, and then you keep going using the leapfrog method. So basically you're jumping one step, so you can keep going that way. But the first step will actually be first order one. All the steps greater than 1 will be actually be a second order one. An alternate method is again this Lax-Van-Roof scheme. This is specifically designed for this particular case. We have Pt can be written as, if you do the Taylor series expansion for phi n plus 1, is phi n plus phi t times delta t plus higher order terms. You can use the governing equation to replace phi t with minus c times del phi del x. That will be this term, where you use a central space scheme for del phi del x. So the delta x, everything will get absorbed into this lambda. And similarly, we have phi tt, which will be minus c square pxx. So again, this pxx is the Laplacian operator, which again you can use the second order for discretization for that. That would give us phi n plus 1. The last method is Max-Cormack. Here, what we do is, in order to update to n plus 1, we will go through an intermediate step. So this is very similar to what we did for forward time, forward space. So phi, but instead of writing this as n plus 1, instead of taking this value directly, we are keeping a temporary step. So you are starting at n, you are going to an intermediate state as if this is a forward time, forward space, and then from the intermediate step, you are going to the next step. So instead of taking one direct step, we are predicting an intermediate step first, and then we are correcting for it. And when we do that, this actually becomes second order accurate in time. You can do the Taylor series expansion for this, and this will actually come out to be second order accurate in time and space. Yeah. Are there any questions or any discussions that you need? Then we'll quickly go through the previous year problems. Maybe you can answer this. Euler's forward time and forward space discretization for this particular dpdt equals minus c pxx, given that c is greater than 0. Which one of this is true? Yeah, you don't have to do von Neumann analysis for this, but which one do you think is true? So first of all, what kind of equation is this? So I'm getting discriminant to be 0. So this is actually a parabolic equation. So which is something that we discussed last week. So it's, in the parabolic form, so this is very similar to the unsteady heat conduction problem, where we have instead of E, we used to have temperature equals to alpha times del square T del x square. In the present problem, here we have alpha equals to minus C and T is T. So if you were to compare these two equations, we are saying C is positive, which means alpha is negative. So we are basically trying to solve an equation which is as if it is a steady heat conduction problem. The only difference is we are having a negative diffusion coefficient. So what would happen physically for this problem? If you have a negative value of thermal conductivity for a material, and I'm trying to solve it is a steady heat conduction problem. So what do you think will happen? Or you can also think it in a slightly different way. So instead of defining this coordinate, I can also introduce a change of coordinate. I can put T star as minus T, and then this equation will be replaced as del T by del T star is with minus alpha, which is basically C times del square T del x square. This is a positive quantity. So this is as if we are trying to solve steady state heat conduction problem, sorry, unsteady heat conduction problem with a positive diffusion coefficient, but then we are actually solving it marching backwards in time. Whichever way you try to understand. So this is basically, if you were to say there is a negative diffusion coefficient, physically, if you have a positive diffusion coefficient, any disturbance at any point, say this is my domain, if initially a disturbance like this exists, then it will actually spread out. So as time increases, so this will actually spread out more and more like this. This is what we would expect when alpha is positive as time increases. But when we have alpha negative, then the exact opposite will happen. So which is basically saying like if this is my initial thing, then it would actually become something like this. And as time progresses, this becomes sharper and sharper, and then eventually you'll get a singularity. So the point that I would like to highlight here is, if the problem itself, the physics of the problem itself could actually be unstable. So in this particular case, the physics itself is unstable. Irrespective of the scheme, like now if we were to use again a forward time forward space scheme for this particular problem, it is going to be unstable. Is this clear? So what happens sometimes, let's say in this particular problem, instead of forward space, I'm giving, since c is greater than 0, let's say I were to use the upwind scheme. What do you think will happen then? So if, for example, for some reason you decided to use an upwind scheme for this particular problem, or any other scheme, let's not call upwind, but let's say use some scheme where you ended up having an artificial diffusion. If it were phi x, then it would have been straightforward because it is phi x x. So we have phi t s minus t times phi x x. And when you discretize this, you ended up in the discrete equation plus some term plus some delta t and delta x. Let's say you came up with some scheme in such a way that it is adding some, because of the grid spacing, that this is the artificial dissipation that I was talking before. And if by some weird chance you have chosen a scheme and a combination of your grid has become such a way that this k is greater than c, then you would end up having a positive value for your diffusion coefficient, and then you will end up having a stable solution. But it is not physical. So we also need to be careful about whether the particular form of equation that I'm considering, the physics of the problem itself, is stable or not. If the physics is stable, then we go ahead with the stability analysis and say and talk about the scheme. So if the physics itself is unstable, then there is nothing that we're going to do about that. Hope this is clear. Any questions? Yeah. Okay. Which of the following numerical method requires two sets of initial condition to solve a 1D hyperbolic equation? So all these schemes are explicit schemes. So which one requires two conditions? Now you might have to remember what is a formulation for each name. Otherwise, answering this type of questions will be difficult. And all of them are actually second order in time and space. So out of these schemes, only the leapfrog scheme actually uses a formulation where you have, in order to get second accurate, we were doing central, just like central space, we'll be doing central time, something of this sort. So it becomes second order accurate, and we use second order space. So when we were using something like this, we would require n plus 1, n minus 1. So instead of the previous step, we need to know the previous to previous step. So when you're trying to solve for this, instead of this, we are actually going one more step behind. So if I were at 0, 1, and 2, I cannot directly solve for 1. I require at least 2 initial conditions to solve for the second step. So we require 2 initial conditions for this particular scheme. And as I said, like you won't really require 2 initial conditions. You can always start from a given step, use a first order accurate scheme, go to the next step, and from there you can use the leapfrog method. Yeah. Which of these is the main disadvantage of explicit schemes in time dependent problems? Marching solution, which means that we are actually solving for one step at a time. Simultaneous equations, small step size or small grid size. As I said, for all these explicit schemes, we have a stability criteria, and we need this criteria to be, we need this value to be within certain limits in order for that particular method to be stable. And depending on your grid size, and that method also introduce other numerical errors, if depending on the spatial grid. In order to reduce those numerical errors, we will end up reducing delta x, and if as I reduce delta x, I also have to reduce my delta t. So the time step size also becomes smaller and smaller. That is the main disadvantage of the explicit schemes. I hope this is a straightforward question. Yeah. What is dissipation error in finite difference methods, and how does it affect the numerical solution of a hyperbolic partial differential equations? The dissipation error introduces artificial oscillations, causing the solution to travel at an incorrect phase speed. What is phase speed? So let's say you have some wave, sin kx minus omega t. This is some wave that is propagating in space and time. Then phase speed is basically defined as omega by k. So what this is saying is the dissipation error is something that gives some artificial oscillations, so that the solution that you see will actually have incorrect phase speed. So instead of ideally what we would want this is to be equal to c. C is just, for example, if I'm solving for phi t minus c phi x equals to 0, then I would expect this as my phi of xt. Then I would expect the phase speed to be equal to c. But because of the way that I've discretized the problem, it is saying that it will actually change the value of omega by k to a different value other than c. So that is first option. The second one, dissipation error causes the reduction in the amplitude of the solution, acting like artificial viscosity. So this I have discussed a little time before. So instead of solving this equation, you will end up having a different equation with some artificial viscosity term, and this artificial viscosity is going to be a function of your grid sizing. So what that causes is very similar to what happens in fluid flows with a finite viscosity. The amplitude gets reduced. Dissipation error leads to excessive growth in solution amplitude, making the solution unstable. So this, as I said, happens only if you have negative values, but depending on the problem, in this particular case, in hyperbolic equations, when we use, let's say, upwind scheme or something, we end up having mu to be positive, and it actually causes a reduction in the amplitude instead of increasing the amplitude. Dissipation error causes both amplitude reduction and phase distortion simultaneously. So this we can see from the Taylor analysis that this is the kind of equation we will end up, where C remains the same, or you can also check in a different way. So I can also write this as e power I kx minus omega t, and then see what is happening for the specific problem. So I have phi t is minus omega times phi, and phi x ik times phi. I can't directly get anywhere from this. But anyways, as you can see from this equation, the value of C is not getting changed. It's only the additional viscosity term that is getting added in this particular problem. So this is actually a reduction in the amplitude and it's acting like an artificial viscosity. Is this clear? Just to check for the last option also. So let's say it says that it causes both amplitude reduction and phase distortion. So what, in order to say whether this particular algorithm or particular scheme causes phase distortion or not, the usual way to go ahead is you assume a particular harmonic solution for this problem, like I just did just now. So you have e power ikx minus omega t, and you substitute this into this equation. So phi t will be minus omega times phi, px will be and we have phi x, which is minus k square times p, and substitute that back here. So phi t is something like minus omega times p, and this would essentially mean that the imaginary quantities have to be zero. So omega is equals to something here, something of this kind. So where speed is actually not going to change. So if this omega by k is a constant, then there is no phase distortion. So which means this particular problem is actually causing us dissipation error instead of the other one, which we call, this phase distortion is called dispersion error. Which is not happening in this particular case. When we are talking about dissipation error, there is nothing in the phase distortion. When phase distortion happens, we call that dispersion error. So dissipation error happens with upwind schemes. As you can see, Navier-Stokes now has all the different kinds of things that we are seeing now. It also has a diffusion term, which where we were solving like similar to like unsteady heat conduction problem, but then because of this advection, it is also kind of having this other scheme is where which we'll keep using in finite volume method later also. Okay. So what value is predicted in the predictor step of the Cormack technique? So this is the Cormack technique where phi star is the value, intermediate value calculated at the next time step. So you start from n, you go to an intermediate time step using forward time forward space, and then you do another step again using forward time forward space like delta t by 2, delta t by 2, and eventually end up n plus 1. So the intermediate step is basically calculated at the next time step, which is at delta t by 2. So it is not at the current time step, but it is at the next time step. And we are only calculating phi star value. So we start from phi n and we go to phi star, and from phi star we'll go to phi n plus 1. So this is calculated as if it is at the next time step. So we are not actually calculating time derivative, we are calculating directly the variable value. I think this is straightforward from the equation. The series expansion used in formulating the Lax-Wendorf method is this. You might have to go through the derivation again. So the one that we already always use is the Taylor series. There are some techniques which actually use the Fourier or other kind of series to come up with different schemes, which we will not cover in this particular course. Here we will mostly deal with only Taylor series. Even in both finite volume and finite difference, we only deal with the Taylor series expansions. So just to kind of remind, the Lax-Wendorf method is where we approximate phi n plus 1 as use the Taylor series phi n plus the time derivative Again, we use the second derivative plus so on. And then we use the governing equation Pt minus C phi x equals to 0. We substitute that into this equation. So this you will replace with minus C phi x, and this you will replace with C square phi x, where phi x you will replace with the central space scheme. Again, this also will replace with the second order accurate finite difference form. And then we will get the resulting scheme is what we call the Lax-Van-Hoff method. So maybe you can do a quick analysis now. So what would be the type of error that we'll get with this? So is it going to be a diffusion or dissipation or a dispersion one? So if I write it in the discrete form, so have phi n plus 1. So if I use a central space, phi plus 1, my minus 1, by 2 delta x, and then we have phi x, which is c square, phi plus 1. So this is the Laplacian operator, which is again second order accurate. And then we have this delta t square by 2. So I can write lambda as c delta t by delta x. Minus phi minus 1 n plus this is lambda square so because this is second order accurate in time and space, like phi n plus 1 will actually be third, but the derivative is like second order. The formulation is actually second order accurate in time and space. So what that means is when we expand this, like use the Taylor series back and substitute this, so phi n plus 1 is phi n plus phi t times delta t plus terms plus lambda by 2. So similarly, if you expand all the terms, because it is second order accurate in space and time, all the delta x square terms, etc., should actually go off. Even delta t, because it is delta t square, the other terms would also go off. So what we would eventually end up with is, if I take delta t common, so I'll have some pt term, and then I'll have a minus c times phi x term. And because it is second order accurate, you will see that I plus 1, I minus 1, this term will actually get cancelled. So in the I minus 1, you'll have phi n. So there will be minus here, plus, and then a minus here. So these two terms will cancel. So I won't have a phi x, the double derivative of phi. And similarly, the only term that I will be left with is the phi triple x one. So even here the same thing, I plus 1, I minus 1, this term's phi double x will actually get cancelled. The double derivative will get cancelled, and we'll actually end up with phi triple x, so which is some constant times this term. So we'll get an equation of this particular sort. So previously when we were seeing for upwind scheme, we ended up having a double derivative. So when we have a double derivative term, and this C1 is going to be function of delta x. So this C1 will be something like C times delta x cubed by 6, or some other factor. Instead of 6, it will be some factor depending on how many terms we add up. So it will be some number here. So but this is something that is a function of grid spacing delta x. So as the grid spacing changes, this value will change. The value of C1 will change, and accordingly our governing equation is actually getting changed. So but what does this mean is, let's say if I were to do the same analysis as before, so have phi t minus c times phi f. This is the original equation, but because of the way I am discretizing, I am ending up having with a new term c1 phi x x triple x equal to 0. So if I have a harmonic solution phi, something like I times kx minus omega t, then if I do phi t, first derivative will be minus I omega times e power whatever we have. Similarly phi x is I k phi phi double x is going to be minus ik times ik is minus k square times phi, and then the last one, when I do the triple derivative, I'll end up getting another ik times phi. If I substitute it into my governing equation, so I'll have minus I omega phi minus c times ik phi plus ik cube phi, because we're looking for a non-trivial solution. So this would give me c, there is a plus somewhere. Okay, because I want it to be positive, this is to be equal minus ikx minus omega t. Okay, fine. So let's ignore that for now. So let's say we have omega plus ek minus k cube equals to 0. So omega by k, yeah, I should have started with phi t equals to minus c times px. Because I started with plus c times px, I'm getting a negative direction. That is fine. So we have omega by k is minus c plus k square. So you can see that this is my phase speed equals to minus c plus some term k square. So this is my actual speed, that is the coming from the governing equation. And then we have this additional k, where k is basically like just like omega is the frequency in time domain, k is the frequency or the wave number. This is kind of a frequency in the space domain. So the phase velocity is actually a function of the particular value of k that we are choosing. So which means if my disturbance has multiple frequencies, like multiple wave bands, so this is my x direction. This is like, let's say there is a pure sine wave, or you can also have multiple components, something like this, something similar going periodically here, which has multiple wave numbers, which is like superposition of multiple things. Then each one will actually have a different wave, a different value of phase speed. So which would mean initially when you started out with, everything will actually move with the same speed, but as you march your time with this particular method, so let's say lax Van method if you are using, and then with this particular discretization scheme, if you try to move ahead, like if you're trying to march in the time, then each wave number will actually move with the speed different from the actual value of c, and that will actually be a function of the wave number, and also the weightage that we are going to give from it, this c1. I think that c1 disappears somewhere. Okay, there is a c1 here, so I should have c1 also here. And this c1 is actually a function of my delta x. So if you have taken a very large grid size, like very large value of delta x, then you'll have more weightage for it, and you will see that as the particular algorithm that you're using is marching in time, these waves will get separated. So in order to reduce this, what we have to do is, one way is reduce the delta x, so use a finite spatial grid also, so that this c1 term will actually get reduced and these waves stick together. Or there is another trick that we usually do, is we also add a dissipation term. So because this extra whatever we have, the dissipation will try to reduce the amplitude of those external, the small deviations that we are going to have, which we are not covering in this particular course, but whoever is interested can actually go through them. How to actually, it's basically straightforward. All you do is in the Taylor series expansion, you add more terms so that in addition to this phi triple x, you'll also have the other term, some phi 4x or something like that. Whenever we have an even power for the derivatives of this, they act as if it is a diffusion. And whenever you have odd terms, they'll add up like dispersion term. You can see that even terms will not have this I term. So they'll just go off. Any odd will have this I, and they'll change the value of omega by k, phase speed. Is this clear? I think that is the next question. Yeah. So that is what dispersion error means. So it does not cause a reduction in amplitude, but what it does is it changes the phase speed of multiple different kinds of waves which are having different wave numbers. So it distorts the phase of the solution, causing waves to propagate at an incorrect speed. We'll also go through other options. So the error which causes reduction in amplitude is basically called diffusion or dissipation. Dispersion results in complete numerical instability of the solution. Dispersion, as I said, it only changes the speed. It has nothing to do with the numerical instability as such. Like there, for example, you can just take this particular scheme that we discussed just now, the Lax-Van-Hoff method. This is actually a stable scheme. It's an explicit method with a stable. The lambda is less than or equal to 1 is the stability criteria. It is actually a stable scheme, but it has dispersion. So the errors won't continuously go on as long as lambda is maintained to be less than or equal to 1. Dispersion error causes loss of information by smoothing sharp gradients in the solution. So whenever these sharp gradients are kind of smoothened, it means that there is some mixing that is happening over there. So this is what we call diffusion, or we also call this as dissipation error. So this is like an upwind scheme. This is what an upwinding scheme does. This has nothing to do with dispersion. So what dispersion does is it just gives different velocities for different wave numbers. Okay. The condition of stability for solving inviscid Burger's equation using Lax method. So Burger's equation is you have ut plus u times ux equals to 0. Just the advection component of Navier-Stokes equation. This is actually nonlinear. So the criteria is very similar. Like even if it is some constant speed, we have lambda to be less than or equal to 1. So which is c times delta t by delta x. But in this particular problem, instead of c, we will take the value of delta t such that the maximum value for the even for the maximum value of velocity, we do not actually violate this particular criteria. So that is the only trick. So all we have to do is replace this c with the maximum velocity that is in that particular in the entire domain. I think this is a straightforward question. I don't think much explanation here. And yeah, these are some generic questions. Which of these apply to hyperbolic equations? As I said, we need the discriminant to be, let's say if I have equation auxx plus uxy plus uyy equals to something, then we need the discriminant to be greater than 0, which will end up, which will give up actually two different y equals to some beta 1x and y equal to some beta 2x. So I'll have two characteristic lines. And these characteristic lines are the lines along which the information actually propagates. Okay. This is the last question. The truncation error for solving first order linear wave with wave speed A equation using a forward time and forward space scheme is. Which of this is true? So forward time, forward space is first order in both time and space. So which one of these is correct? So first we need to understand what is the governing equation that we are solving. So first order linear wave with a speed, what is the governing equation? So we are having u. This is the governing equation. All we have to do is do the Taylor series expansion, and then we can get this. So we have delta t So can you quickly tell me which one is the correct one? So if you do Taylor series expansion for ut, this is basically ut plus delta t by 2 times u2t plus, so you can directly expand from here only. You can say that there is for this we need to have a delta, this delta, you can multiply this entire thing with delta t, or you can just do a forward time is uin plus 1 minus uin by delta t. Forward space is ui plus 1 n uin by delta x. So for this you have to calculate the truncation error. So you can take the entire thing on the right hand side or left hand side, and then you can see that here this is something like ut plus, so uin plus 1 will be uin plus ut delta t plus utt delta t square by 2 u triple t delta t cube by 6 and so on, minus uin by delta t is minus a times ui plus 1 is again similar uin plus ux delta x uxx delta x square by 2 uxx delta x cube by 6 and so on, minus uin divided by delta x. So truncation error is basically the one that remains after you take the original equation. So we have ut and we take the other side, other term here, minus a times ux. If we take on to the LHS, so we have minus this minus delta t by 2 minus delta t square by 6, so on, and then we have here minus a delta x by 2 and so on. I think okay, so this they would have taken to the other side. So this entire term taken to LHS will become the truncation error. That is option number 4. Is there any question? I think this is a straightforward one. I don't think there are any questions. So now we'll take up some coding to actually see how this is one that is already discussed in the lecture. We'll just try to vary the stability parameters and see how this actually changes our solution. Just let me show the problem. So the problem we are having is the same 1D wave equation with the speed as 300 meter per second and the boundary. So we need a one initial, when we have this problem, we need the boundary conditions and the initial condition. So the boundary condition we are saying periodic, which means if you have a domain like this, so this is say I1, 2, so on. So when we say periodic boundary condition, we mean that 1 and values of n are essentially equal. So that is what a periodic condition means. And what that would mean is like you don't have to actually solve for 1 to n. You only need to solve for 1 to n minus 1. So this will actually be the variables that I will be solving for. And then we need initial condition, which is initially in the total domain. For most of the reason it is 0 initially, and then there is a sine curve. So we have something like this, and then it goes 0. So this is the disturbance initially that is present. What we are trying to do is we are trying to solve the problem from t equal to 0 to t equal to 1. So what happens is, because this is a hyperbolic equation, information moves in one direction. So this we expect this to move because c is 300, which is positive. So we expect this to move in this direction. And we try to solve this using, this is an explicit method. These two are explicit methods, but this is first order accurate in time, this is second order accurate in time. And this Crank-Nicolson is the implicit method. And then we need to see what is dispersion and dissipation errors in the solutions. Which one of them will have dispersion? We didn't actually discuss about the Crank-Nicolson method, but the idea is same. You do the Taylor series expansion and you see whether the truncation error has an even derivative. If it has even derivatives other than the governing equation, if it has an even derivatives, then that particular scheme is going to give us the dissipation errors. If it has an odd, if it has odd derivatives, then that is going to give me dispersion errors. Let's see how to implement this in code. So let's start with forward time, backward space. As I said, we are not doing forward time, forward space because that is unstable for this particular problem. With c greater than 0, this is an unstable scheme. So we'll only use the forward time, backward space. So these are the parameters that are given to us. C is 300 meter per second. The total domain length is 300 meters. I'm integrating up to t equals to 1. Dx I'm considering as 1. This is something that you need to vary and try. Lambda is our stability criteria. It has to be less than 1. I've taken 0.5. So this is basically the current number that we are talking about previously. So from this current number, we will calculate the delta t, that is so that the solution is stable. So lambda is c delta t by delta x. So delta t is lambda times delta x by c. So what this line does is it just creates a domain. It creates a domain like this between 0 to L with the 1 unit length as dx. So as I said, we are only solving from 1 to n minus 1 because for a periodic boundary condition, we don't need to solve for n separately. N is basically 1. So I'm creating a grid only up to L minus delta x. So instead of solving till L, we'll only solve till L minus dx. So this line creates that. N is basically the length of the grid that I've created just now. U is a variable that we are trying to solve for. Here I've created it as a matrix of t times n. So my rows will be different time instance and columns is basically my space coordinate. So you have a matrix like this where each of these rows is my time coordinate equal to 0, delta t, 2 delta t, etc. And these are my x coordinates. So this is how I'm storing the solution variable. You don't ideally have to store all the time steps usually. The first function is to initialize the value of u. So this is in Julia, what we do is we add this exclamation just to say that you don't store the copy, you change the actual value of the array itself. So when I write u equal to initialize u of u, this actually does it in place. So first we are creating a mask. So based on the function that we have, for 0 to 50 it is 0. So only between 50 and 110 we have a pulse. So in order to say that, we give the criteria 50 to 110, we create a mask, and then only for those values at initial time, at the 1 is basic. The indexing in Julia is very similar to is basically like MATLAB. So it starts from 1 instead of 0 like Python or C or any other languages. So for the t equal to 1, we have the profile that is given to us 100 times sine pi times x minus 50 by 60, and then you so initialize the u. And we define now the interior grid points, which is from 2 to n. These are all my interior grid points. So ignore these lines for a moment. I'll just explain them a little later. But the algorithm scheme is here. We have the forward scheme where ui n plus 1 is basically 1 minus lambda times ui n plus lambda times u. Maybe I'll write it here so it will be clear. So we're dealing forward time, backward space. So the scheme goes like ui n plus 1 minus ui n by delta t is minus c times backward scheme. So this will be ui n minus ui minus 1n by delta x. So this is backward space. So if lambda is c delta t by delta x, this becomes ui n plus 1. It's 1 minus lambda times ui n, and then we have lambda times ui minus 1n. So this, if I were to write in the matrix, u times the row is n plus 1th row, column is I, is 1 minus lambda. So as I said in the last week, so here we have to iterate to each and every along the x direction. So for each and every value of I, we have to do this. And all these values, we have already calculated the values at the previous time step. So everything on the right hand side is already available to us, which means we do not have to actually, like the for loop goes in a sequential way, which we do not have to do. Because all the data is already available to us, we can actually do some vectorization trick. If you are using in Julia, the way is you write it in this particular fashion where you give all the interior coordinates in one row, 2 to n. It does all the vectorization inside. So basically what it does is it calculates Instead of writing a for loop, it calculates all of them in one go. So for all the interior cells ui n, un plus 1 I is 1 minus lambda times un I plus lambda times un I minus 1. And then for the boundaries, what changes here is in this equation, whenever I'm at the boundary, I do not have an I minus 1 term. So basically at I minus 1 for this, because of periodic boundary condition, will become the last coordinate here. So I minus 1 for this should reflect to this one. So what that changes is this remains the same. But the other one becomes, instead of I minus 1, this will become whatever is the total and the n. Because, okay, I use n minus 1. Okay. N minus 1. And I do not have to worry about this one because whenever I'm at the n minus 1 grid, I have n1 already available to me as 1. Like because it is a backward space, when I'm solving for this, it will only refer to the n minus 2 grid. Like when I'm at nth cell, it is basically equal to first cell, so I don't have to solve for that. So I'm solving only till n minus 1. At n minus 1, it will refer to n minus 2 cell, so I do not have to specifically add a separate loop for that. That is already kind of included in the interior cells. So in the interior cells is 2 to n, where n I have taken up to L minus dx only. Just a slight mismatch between the code and the one that I have shown with anti-10. But I think there are no confusions in this. So all we have to do is make sure that I plus 1 is basically an n coordinate, so that the periodic thing gets set up. So once this is done, all we have this is just a plotting one. So I'm not running this before, so I've already run this before. Okay, I don't have this. Just run this one. Dissipation error. So this is how it looks. This is lax one drop. Sorry. So yeah, this one. So you can see that when we use upwind scheme, you can see the reduction in amplitude as the disturbance propagates as a function of time. So this is what I was calling the dissipation error. So whenever you use a backward scheme, we have that the truncation term has a double derivativity, which is an even term. So we'll have a dissipation error, which basically reduces this. And you can also see the other problem is how these values are not sharp at the boundaries. So there also some kind of smoothing happens. So whenever there is a sharp gradient, what this dissipation does, it will reduce the sharp gradient, and then this actually becomes smoother like this. So this is a dissipation error. Are there any questions? And these are other this kind of macros that we use just to kind of generate the animation. So we can ignore this part. The only things that to focus on is this part, where we kind of did something called vectorization, which is ensures that this update is happening in parallel. Are there any questions? I think this is straightforward, right? Now the same problem, if you want to solve with Lax-Van-Drop scheme, the only thing that like everything else remains the same. Now we have 3 additional terms here from the scheme itself. So this is the Lax-Van-Drop scheme. So if you were to club the terms together for Phin, so I will call it as C1 times Phin, so which has a 1 here and then minus lambda square here. So C1 is 1 minus lambda square, and then let's say C2 times Phi plus 1. So Phi plus 1 has a lambda square by 2 minus lambda by 2, and then a C3 of Phi minus 1. So this will be having lambda square by 2 plus lambda by 2. So this will be my C1, C2, C3. So 1 minus lambda square, lambda square minus lambda by 2, and lambda square plus lambda by 2. So this will be my C1, C2, C3. And accordingly, now I will update my interior points, which is un plus 1 at I is C1 times uni, C2 times uni plus 1, and C3 times uni minus 1. So you might have noticed this dot I'm keeping everywhere. So this dot will basically say that you have to do this operation element by element. So this is how it kind of interprets the vectorization that I was talking about before in Julia. This is something that people who are familiar with MATLAB might be familiar with this way of writing the program. And then now we have the boundary nodes. So unlike the previous problem, now we have two different boundaries that we need to take care of. So when I'm at the left boundary, I do not have any I minus 1 term. So I minus 1 is basically my end coordinate. So I'll just write n. So I will be 1, I plus 1 will be 2, and I minus 1 is basically the last one. So because of the periodic boundary condition, I have to just write n here. Now similarly for the right boundary, I is the last boundary, so I will be n. I plus 1 will be, instead of n plus 1, it will actually go to the first coordinate. So this will be 1, first index, and I minus 1 is basically n minus 1. This is the only difference that happens. So in the backward space, we do not have to worry about the right boundary because it only refers to the back coordinates. So I always have n and 1. I do not have n minus 1 to take care of there. But because here we are having, in ax and rho, we are actually having both the kind of a central space thing. So we need to take care of both the left and right boundaries. And everything else remains the same. If you see the solution, you can see these additional terms that are coming here. So that is what we are calling dispersion. So some noise, whatever that happens, which is propagating at a different speed, will actually cause this additional waves coming up into the solution, which are not true, which are kind of artificial ones that are introduced. So now if we do have diffusion into this, as we saw in the dissipation error, the amplitude gets reduced, right? So what we want to do is there are some schemes which actually do some clever balancing between dispersion and diffusion. So eventually these small peaks that we are seeing here will actually damped out by the artificial dispersion that artificial dissipation that was created from say the affine scheme kind of thing. So by balancing these two, there are some schemes which can actually reduce both the dispersion and dissipation errors also. So both of these are explicit methods. So I will be solving for only one variable at any given point of time in one given equation. Now let's say if you want to do Crank-Nicolson for this. Let's say I want to implement Crank-Nicolson scheme. Maybe I should write the equation first, then it will be clear. So how would Crank-Nicolson look for this problem? So have ut minus cux. So this will be ui n plus 1 minus c by 2. So ux I will take both the implicit form and explicit form. So first the implicit form is ui plus 1. So central space. So it will be at n plus 1 step. And then I'll also take the explicit form. Again central space. So this is second order accurate. If we define lambda as c delta t by delta x, so this essentially becomes ui n plus 1 is ui n minus c delta t by 2 4 delta x. So this is lambda by 4 times ui plus 1 n plus 1 minus ui minus 1 n plus 1, and then I have minus lambda by 4 ui plus 1 n minus I minus 1 n. So if I just take the separate this into known and unknown components, all the values at n plus 1 are unknowns and all the values at n are known. So if I were to take terms together, so this will be lambda by 4 times u I minus 1 n plus 1 plus ui n plus 1. Okay, there is a minus plus, so this will be minus and just plus lambda by 4 ui plus 1 n plus 1. Equals on the other side we have again I minus 1 lambda by 4 times ui minus 1 n plus ui n, and then we have for I plus 1 minus lambda by 4 ui plus 1 n. So this is essentially, again you can see for all the I. So if I were to write it as a matrix, so this will be like initially it will be 1 lambda by 4 0 etc etc, and then for I minus 1 term the coefficient will be minus lambda by 4, ith term it will be 1, I plus 1 it will be lambda by 4, so on. This keeps going. So this is a tridiagonal matrix. So I'll call this matrix A times the values of u that we are solving for. Similarly, we have the same matrix here. This is also again a tridiagonal matrix that we are solving for here. This matrix will also be similar. The only difference is, say ith term is 1, I plus 1, instead of lambda by 4, we have a minus lambda by 4, 0 so on, minus lambda, sorry, plus lambda by 4, 1, minus lambda by 4, 0 so on, so on, so on. So this is again another tridiagonal matrix. So which we'll write it as B. This we are solving at n plus 1. This is at n, un. So we know the value of un. We can construct this matrix, and all we have to do is a times un plus 1 is bun. So once we have this matrix, like b times un will give me the matrix B. So it is of the form Ax equal to B, and then we can use whatever solvers that we discussed before. You can use a direct solver, or you can also use some iterative solvers like Gauss Seidel or any other method that we discussed before. For now, we will restrict, like, because this is, we know that it's a tridiagonal matrix. All we have to do is use Thomas algorithm, and then we can solve this. And in Julia, there is this packaged linear algebra that has all these solvers in it, which uses we can directly solve from there. But this is for the interior cells. Now, what happens at the boundaries? Let's say at the left boundary, because the index notation is, we are starting from I equals to 1 to n plus 1 is basically equals to 1. So this is a circular mapping that we have because of periodic boundary condition. So at the left boundary, which is I equal to 1, what will happen to the equation? I do not have this I minus 1 will be, so in the governing equation we have minus lambda by 4. So I minus 1 is basically going back to n. So this will be un n plus 1 plus I is basically 1 plus lambda by 4. Everything else remains the same. So u2 n plus 1. Same goes here. I minus 1 will become un. So what this means is, in the matrix that I have created before, now we are kind of doing a little change here, where we are adding this, the additional term that is coming here, which means this will act, so in the matrix U here, we'll have u1, u2, so on, un, this is a 10 plus 1, similarly we have u1, u2, un, 10th step. So now we have a coefficient for un term. So this modifies the matrix form originally that we have here. So what this changes is, I'll have an additional minus lambda by 4 that is coming in the last term here. Similarly, on the right boundary, what happens? Same thing here also. It changes both on left and right hand side. So even in this matrix, we'll have an additional term for lambda by 4 that is coming in the last coefficient. So for un coefficient, this gets multiplied with this lambda by 4 term. So now on the right boundary, we have I equals to n. So I minus 1 is straightforward. Un minus 1, un, I plus 1 becomes 1. Plus u1 u1 minus lambda by 4 u1 n. So what the second at the right boundary, what happens is, now we are having, like, this will be 1, this will be minus lambda by 4, and now we also have a contribution from u1 term. So the first coefficient will be lambda by 4. And here it will be minus lambda by 4. Everything else is zeros, and we have plus lambda by 4 and 1 coming for un is 1, and un minus 1 is minus lambda by 4. Oh, sorry, un minus 1 is lambda by 4. That is coming here, and the contribution from u1 is adding this extra term lambda by 4 here. This will be the, so these terms are the additional terms that are added because of the periodic boundary conditions. They are kind of changing the structure of the matrix. But this doesn't affect how we solve Ax equal to B. We can directly use the iterative methods that we have before. But implementing with Thomas algorithm, there is some little problem. But the way the matrix is constructed is clear, I guess. If that is clear, then implementing it to code is straightforward. So we have this alpha. I'm defining alpha as lambda by 4. This lambda by 4 I'm calling alpha, so I can create my matrix accordingly. So A is a matrix, so this tridiagonal is a function that is directly available. So what this tridiagonal function does is you have to specify, so tridiagonal matrix is like you have something like this, everything else is 0 in the matrix. So you have to specify these three elements directly. The first one is the subdiagonal, superdiagonal, and the diagonal elements. So all the subdiagonal elements is minus alpha for A. So these are minus alpha, 1 and alpha. Here it will be alpha, 1 and minus alpha. So that is what I have created here. So A is a matrix with minus alpha as subdiagonal, diagonals are 1 and the superdiagonals are plus alpha. So once the A matrix is created, now we have to take care of the periodic boundaries. So for the first case, we have the last boundary getting changed to minus alpha, and for the last case, the first one is getting changed to alpha. Similarly for matrix B, just that alpha will be reversed because on the right it is getting transferred on the right hand side. So this will be alpha, subdiagonal once and minus alpha for the superdiagonals. Once I have A and B matrices, this is just a trick. People who are familiar with linear algebra would have know what there are different kinds of ways of factorizing the matrix, which we are not discussing in this particular course. But what they do is what we are trying to do is we are trying to solve for the matrix Ax equal to B. We are trying to find a solution for this. So each time we are doing x equal to A by B, or basically we are not actually doing A inverse B. We are doing some other way. So what factorization does is in this particular problem that we are solving, the value of A is not changing. Lambda by 4 or whatever alpha that I discussed, this matrix A is not changing. So which means we can actually use some kind of trick to save our computation time. So that is what we do with factorization. Once we do factorization, it will store the factorized matrix, and I will always use this factorized. So this can actually be faster with the factorized form. Explicit we discussed just now. So this is the upwind scheme. So 1 minus lambda times 2 to n, and this is I minus 1. The backward space, forward time. Implicit, you just do the A inverse kind of field. So it's basically not A inverse field. You use some iterative solver internally. So this is a direct solver. The one this method actually does a direct solver, and then we visualize both of this together. So implicit, explicit, and show that here. You can observe few other things also, how this dispersion is happening here, and you can also see like the other thing is about how this gets spreaded out. But the point I would like to highlight is about the stability. I should have done the stability. Okay. So this lambda is a stability criteria. For the forward time forward space scheme, the stability is basically lambda is less than or equal to 1. And I have taken 0.5, so this is correct. But if I were to use, let's say, higher value, say lambda equal to 2 or something, yeah, you can see what happens to the solution. So this just keeps exploding. So, but the implicit scheme is still giving me some result. Of course, the accuracy is a problem. If I keep increasing the value of delta t, then beyond a point, like it will still be stable. I'll get a finite value. The only question is it won't be accurate. So we have to balance this thing. And this is always expected, so this is not a big problem. Then we'll move on to. Are there any questions in this in the implementation part? Okay. Then we'll just do a small thing. This is just to show the dispersion and dissipation errors. Let's take the same problem as follows. Just to the only thing is now to how to handle different kinds of boundary conditions. So previously I gave a periodic boundary condition, but usually we'll have problems with say dirichlet normal or mixed condition. Let's say we have a different kind of condition. Then how does this formulation change? This remains the same. The only difference is how your left and right boundaries are treated. How will that change? Let's say we have to solve, just duplicate this. Everything else remains the same, but let's say at the left boundary, let's say instead of we have, yeah, at x equal to 0 we have this. So this is a Dirichlet condition. So what this means is we are essentially giving a pulse. At, for t less than or equal to 0.5, we are giving some input. After that, we are actually stopping it. So there is some kind of input, that is source that is coming for a given amount of time and it stops after that particular time. So at x equal to 0, and other end is outflow. Outflow is basically means ux equals to 0. Yes, this is basically Neumann condition. How this gets translated into the matrix form? So in my matrix, so this interior points remains the same. Now at the left boundary, I have a fixed value. So what happens to this? For Dirichlet condition, so when I say Dirichlet, we are actually specifying the value of u or c, whatever we are trying to solve for. So which means we do not have to solve for this particular variable at all. U1 is something that we do not have to solve at all. If you are not trying to solve that, then we don't need any coefficients here. So basically all these coefficients have to be 0. So the entire first row, we just replace with zeros. Whenever we have Dirichlet condition, because we are not actually solving for that. Or except for the one that, so basically it becomes something like zeros except at that particular column. So here u1, so first one will be 1 and everything else becomes zeros. And in the b term, you'll make sure that the corresponding value of the Dirichlet condition is available at that location. So that will be the source term that we are adding to it. So you'll add whatever is the source term that you have given it, u of x0 comma function of time. So what this means, it will translate to u1 equals to whatever is the value of u1 calculated at 0 comma t. So we do not have this lambda before all these things. We are not actually solving for anything else because the value is already given to us. Now at the right boundary, what happens? We have an outflow problem. So what happens in the right boundary? So again, we have to choose a corresponding scheme. So let's say if I use just like what we were doing before. So we will use a scheme. Let's say if we are okay with the first order spatial scheme. So all we have to do is ui plus 1 equals to ui, sorry, un at n plus 1 equals un minus 1 at n plus 1. So instead of this whatever equation that we have here, all we are writing is un plus 1 equals to un minus 1. So this will be my, or in other words, this will become un n plus 1 minus un minus 1 n plus 1 equals to 0. So my last row will basically become everything is zeros except n minus 1 term I'll have minus 1 and then nth term I'll have a 1. So all this matrix will be same as before. So this will be un minus 1 term, un term, and here we have to ensure that everything is zeros. So this is how the matrix A comma B will change. Depending on, this is for Dirichlet condition, you just have to make depend everything else 0, and right hand side you have to ensure that whatever source term, whatever the boundary condition you have to enforce that boundary condition in the beta. For Neumann condition, so this won't be the governing equation at all. The new governing equation, this is again first order. This will be, if it is a second order, you have to use accordingly the second order scheme. Then you will have different coefficients of minus 1 1, you'll have minus 3 by 2, the ones that we derived last week. I think this is clear. Implementation is again straightforward. It's very similar as before. So let's say I don't have second order scheme here. Okay, I have it. As I said, like all the terms will be 0 except the coordinate that we are trying to solve for, it will be 1. These terms you will make it equal to 0. And as I said, we need to add the source term. That in our particular problem, what happened is the source term is actually a function of time. So I have to update it at every time step as I march. So initially I'll make it 0, and then eventually I'll add it. I'll keep adding it here into the source term. RHS of 1 will be whatever the source term that I'm solving for, where source term is calculated from this equation, 50 sine 2 pi times 5t for t less than equal to 0.5. Otherwise, it is equals to 0. And the right boundary is the outflow condition. Is just as I said, I'll use again using first order scheme. We have u, so we have a -1 here and a +1 there. So I'll have to make last one to be 1 and n minus 1 to be -1, and accordingly I have to update my bn. Bn is basically 0 in this particular problem. Like for this scheme, as I said, like everything else is 0 on the right hand side. That is what I have written here. Once we do this, all we have to do is solve this set of equations. I have updated my RHS and LHS. U is calculated using iterative direct method, whichever you choose. Here, this is a direct method. You can use any other iterative solver you know and solve the problem. So now the interesting thing is if you were to follow this one. So this is a source term that I have given that is getting propagated up until 0.5 seconds. After 0.5 seconds, it just stops. But you can see the kind of errors that we are having at this, wherever there is this gradients, we have this dispersion error. Now what happens is that dispersion error also propagates. So this is basically the noise that is traveling at a speed different from the actual waves. You can see how the noise actually propagates. But the point that I would like to highlight here is the dispersion error is not actually causing the algorithm to blow out. So this method, because we are using Crank-Nicolson method, which is inherently stable, even though there is this noise that is propagating here and there, it's actually not causing it is not causing any blowouts. In order to reduce this, now we have to either use a scheme which is higher order in spatial accuracy, or we have to reduce the delta x. So let's say if I reduce this delta x to 0.5, yeah, but what we would ideally expect is if I were to do this, then the dispersion error that I am getting here, the error that is propagating backwards, should actually get reduced as I reduce my delta x. I think this is getting updated now. In the meantime, we'll also expand this problem. Let's say if I were to expand this to a 2D case, what would change here? Let's say I want to solve a 2D problem. 2D problem will be, say, ut is minus c times something like ux plus uy. Let's say I have something like this in a 2D form. And then the classic problem is you have some surface and then you have a Gaussian droplet falling on the top. So initially it will be like very high value in the center, and then it keeps, how does this thing get propagated? If it is a parabolic, then what we would expect is instead of u double t, if you have just ut equals to something like this, then what we would expect is like a unsteady heat conduction problem. So temperature will be something like this initially, and eventually slowly it becomes uniform throughout. That is what we would expect if it is a parabolic. But because this is a hyperbolic problem, what happens is something different. So this, it actually split it. We will have, let's see the code first. I think this is completed. I'll update this in the folder. We'll go to the 2D wave problem. So everything else remains the same. The only difference is now we have instead of I and j, now we also have I plus 1. Like instead of just the I coordinate, we have a j coordinate. So this will be the east, west, north, south kind of thing that we did before, just like unsteady heat conduction problem. Just that we are also doing in the time domain. So u next is the temporary variable that will store the value of this. Is the current value un minus u old is the previous value, where u now you can see is initially I'm initializing with a Gaussian profile, which is exponential of minus x square plus y square by 2 sigma square. So this is some particular value of sigma I have given. and you can see what happens is something like this. So the disturbance, instead of everything becoming, you can see that all the interior points actually become 0, and this keeps propagating. I've just kept reflecting boundaries, so you see all these kind of patterns, but otherwise you can keep other boundaries also. But the implementation wise, the only difference is now we have this instead of I plus 1, I minus 1, these were the only ones we were having before. Now we have j plus 1, j minus 1 terms. So extending this to 2D or 3D is actually straightforward. All these time matching methods are straightforward. Now, if this was an implicit, like this is an explicit formulation, if I were to use implicit formulation, then I have to populate the matrices and then solve for them accordingly. But this is an explicit, and I've taken a lambda value accordingly. I've taken a lambda value of less than 1. Yeah, this lambda value is actually less than 1. Are there any questions? I think there is nothing to ask in this. All the implementation is like just as this one, forward and backward space. The only difference is instead of I, now we're having I and j, and I'm not storing all the time values, just plotting them as and when they occur. Yeah. To summarize what we discussed in today's sessions, we started out with examples for hyperbolic as advection, wave equation, and so on. And then we discussed two kinds of matching methods, either explicit or implicit methods. In explicit, we discussed different techniques for different order of accuracies. These are all first order accurate in time and space, and then second order accurate time and space method. This is also actually Max Cormack also comes here. This is also second order time accurate explicit method. And then we discussed implicit methods, backward time central space, and Rank-Nicolson method. This is first order accurate in time. This is second order accurate in time. Then we discussed some about dissipation error and dispersion error. So the conclusion is whenever you have the truncation terms which have a double derivative or some even order derivative, then that causes dissipation, and anything that have odd order derivatives will give us the dispersion error. So dissipation error reduces the amplitude, kind of smooths out everything. Dispersion error, on the other hand, gives some kind of extra wiggles inside our solution, which are basically the noise that is having a different wavelength that is traveling at a different speed from the original solution. The way to reduce them is use a finer grid or use some kind of artificial dissipation, and it's like add some extra dispersion, add some artificial dissipation, and some kind of balance between these two so that you would end up having the accurate solution. There are other techniques also called spectral methods, which actually use a different way to completely avoid this dispersion error, which is not covered in this particular course. Yeah. Then we have seen how to implement this in Julia. Like programming language is not a choice. As long as you know how these matrices are populating, you can be able to solve them yourself for implicit methods. Explicit is actually straightforward. If you know the equation, then writing that is straightforward. Yeah, these are the things I have for this week. There are no questions, then I think we can end the session for today. Yeah, I guess there are no further questions. Thank you for joining. We'll meet again next week, same time. Next week, we'll discuss about the stability analysis also.